In this video, I'm going to go through how you integrate an algebraic improper fraction. So first off, we need to discuss what an algebraic improper fraction actually is. So we'll start off with a numerical improper fraction and then adapt the definition for an algebraic one. So for example, 9 over 2 is an improper fraction, and that is because our numerator 9 is the same as or greater than our denominator, which is 2. In comparison, for an algebraic improper fraction, which we've got written over here, this is when the highest power in the numerator is the same as or greater than the highest power in the denominator. And when I'm talking about power, I'm referring to the power of our variable, which for my algebraic fraction is x. So let's just verify this is indeed an improper fraction. Well, the highest power in my numerator of x would be 2, and then the highest power of x in my denominator would be 1. So therefore, since 2 is the same as or greater than 1, we have an algebraic improper fraction. Now, when we're talking about these, we're only talking about positive integer powers. Okay, we're not going to consider negative powers or fractional powers. And what we're going to think about is how do we actually integrate this fraction? So first, let's just establish why we can't use some of the methods we've discussed in previous videos. So one option we've used for fractions previously is when the denominator was a single term, we tried to split it up into multiple fractions with the same denominator. Here we have x subtract 4. Okay, we got multiple terms. We got the x and then the subtract 4. So we're not going to use that method. Now another method was to rewrite it using indices laws. So our denominator x subtract 4 is raised to the power of 1. So if I was to rewrite it using indices laws, I would get my numerator 2x squared subtract 6x plus 3 multiplied by my denominator x subtract 4, but raised to the power of negative 1 instead. Now, we don't want a power of negative 1 when we're integrating, because if I add 1 to that, I get 0, and then we're going to have to divide by that power. And you can't divide by 0, that's undefined. So therefore, we don't want to use indices laws. Now, another option we could consider when our denominator is raised to the power of 1 is the natural logarithm. So what we could do to check whether we can use the natural logarithm, we could go to our denominator x subtract 4, and we could differentiate it, which would give me 1, and then ask ourselves, is this a numerical multiple of our numerator? And it's clearly not. To get from 1 to 2x squared subtract 6x plus 3 is going to involve something with x in it. So therefore, we can't use the reverse chain rule and the natural logarithm. And this is always going to happen for improper fractions, because for the derivative of the denominator to be a numerical multiple of the numerator, we need them to have the same highest power. And we know by the definition of an algebraic improper fraction, the highest power to begin with in the numerator is always the same as or greater than the highest power in the denominator. Therefore, if I was to differentiate my denominator and reduce the power by 1, we know those powers are never going to be equal to each other. So therefore, our derivative of the denominator, which in this case was 1, is never going to be a numerical multiple of our numerator. So therefore, we can't use any of the methods that we've discussed previously. So another option which we're going to use for algebraic fractions is to rewrite it using division. So if I was to go to our improper fraction of 9 over 2, well, the calculation I could do is 9 divided by 2, which would give me 4, remainder 1. So therefore, I could rewrite 9 over 2 as 4 wholes, which is our quotient, plus our remainder 1, divided by 2, our initial divisor, because the idea that remainder 1 has not been divided by 2. So let's do something similar for my algebraic improper fraction. So we're going to have to do algebraic division to figure out our quotient and our remainder. So I'm going to set up my division, and I'm going to put the 2x squared subtract 6x plus 3 under here, because that's my numerator, which is going to be divided by my denominator, which is the x subtract 4, which I'm going to write out here. So then to carry out my algebraic division, what I'm going to do is take the 2x squared, and we're going to divide by x. So 2x squared divided by x would be 2x. So I'm going to write that in my x column over here. Then what we do next is take our 2x and multiply it by the x subtract 4. So 2x times x is 2x squared. And then 2x times negative 4 is negative 8x. Then we're going to subtract to get my remainder. So if I put a subtract here, so we'd do 2x squared subtract 2x squared, which is 0x squared. And then we're going to do negative 6x subtract the negative 8x. So subtracting a negative is addition. So we're going to get positive 2x. Now the power of x here is 1. The power of x in my divisor is also 1. So since they match each other, we have to keep going. So my next calculation is to do the 2x divided by the x, which would give me positive 2. So I'm going to write a plus 2 in my constants column. And then what I'm going to do next is take that plus 2 and I'm going to multiply it by the x subtract 4. So 2 times x is 2x, and then 2 times negative 4 would be negative 8. Then the other thing I have to remember to do is to carry down the plus 3, which is the constant here. Okay, so if I carry it down to here, I would get 2x plus 3, and then we have to subtract to find the remainder. So we'd have 2x subtract 2x, which is 0, and then we'd have positive 3 subtract negative 8. Subtracting a negative is addition, so we have 3 plus 8, which gives me 11. So now the power of x in the 11 is 0, whereas the power of x in my divisor was 1. So since we've gone below that 1, our division has now ended, and the 11 is the final remainder for the division. So I can now rewrite my initial algebraic fraction. So my initial fraction was the 2x squared subtract 6x plus 3 divided by x subtract 4. And I can rewrite that as equal to my quotient, which was the 2x plus 2. And then we've got our remainder 11 at the bottom here, which we're going to add on. However, the idea is we haven't divided that 11 by our divisor x subtract 4. So therefore we would have 11 over x subtract 4. And that would be the fully rewritten version of my initial algebraic fraction. So now let's write that expression into my integral. So my integral would become the integral of the 2x plus 2 and then plus the 11 over x subtract 4. And then we'll put it in brackets because it's multiple terms, and then we got a dx. Now let's go through and integrate each term individually. So for the 2x, well, that's a standard first year integral, since we got our variable raised to a power multiplied by a numerical value. So we'd add 1 to the power to get x squared, and then we'll divide the initial 2 we had here by our new power 2. So 2 divided by 2 gives me 1, so we're just left with x squared. Then our next term is a constant plus 2. If I integrate that, I'm just going to get 2x, so I'm going to write in plus 2x. Then we've got ourselves a different fraction over here. So let's consider which method we can use on this. So our denominator is still raised to the power of 1, so we're not going to use indices laws. But now let's check again whether we can use the natural logarithm. Okay, because if I differentiate the x subtract 4, I get 1. And the 1 is a numerical multiple of the 11 in my numerator. Since to get from 1 to 11, we would have to multiply by 11. So we're going to make use of that 11 in my answer. So the integral would be plus 11 multiplied by the natural logarithm of the modulus of my denominator x subtract 4, like that. And of course we need a plus c, and then that would be my complete final answer to the integral in this question. Let's have a look at a different question. So here's our next integral, and let's verify once again that this is an improper fraction. So let's go to our numerator and identify our highest power of x. Well, that's going to be x to the power of 1. And then let's go to the denominator and identify our highest power of x. Well, that's also going to be 1. Okay, and 1 is the same as or greater than 1, so therefore the highest power in the numerator is the same as or greater than the highest power in the denominator. So we have ourselves an algebraic improper fraction. So let's start by doing algebraic division. I'm going to take my numerator 5x subtract 4, and then divide by my denominator 3x subtract 2. So we would start by doing the 5x divided by the 3x. Okay, so 5x divided by 3x. The x's cancel, so we're just left with 5 over 3, which I'm going to write in my constants column. And then we would take that 5 over 3 and multiply by the 3x subtract 2. So 5 over 3 times 3x would give me 5x. And then 5 over 3 times negative 2 would be negative 10 over 3. Then we're going to subtract to find our remainder. So 5x subtract 5x is 0x. And then we've got negative 4 subtract negative 10 over 3. So subtracting a negative, that's going to be addition. So we're doing negative 4 plus 10 over 3. So that would give me negative 2 over 3. But the power of x in negative 2 over 3 is 0, whereas the highest power of x in my divisor over here was 1. So that means we have gone below that power of 1, so our division ends there, and the negative 2 over 3 is our final remainder. Now let's write out my rewritten version of my initial fraction in my integral. So I'm going to rewrite my integral as the integral of, and it's going to be my quotient, which is the 5 over 3, and then plus our remainder, which is the negative 2 over 3. But since our remainder is negative, I'm actually going to replace this plus here with a subtract. Okay, but then I'll write my remainder 2 over 3 divided by our initial divisor, which was the 3x subtract 2. And then since we got multiple terms, I'm going to put it in brackets and then put dx here. Now let's have a go at integrating each individual term that we've got here. So just because we have a fraction within a fraction up here, I'm just going to rewrite the integral just to make it look a bit neater. Okay, I'm going to rewrite this as the integral of 5 over 3, our first term, with respect to x, and then subtract the integral of our fraction here, 2 over 3, divided by 3x subtract 2, with respect to x. Because we got subtraction between the terms, we can write it as two separate integrals. And then I'm going to go further and just factor out the 2 over 3 in the numerator here. So I'd have the integral of 5 over 3 with respect to x, subtract 2 over 3, multiply by the integral of 1 over 3x subtract 2 with respect to x. You don't have to do that, but it just makes it look a bit neater. So let's go through and carry out these integrals. So the first one is the easy one. Okay, if we have 5 over 3, that's a constant, so that's just going to become 5 over 3x. And then for my next integral, I'm just going to write in the negative 2 over 3 so I don't forget about that, because that's going to multiply my final answer, which I'll put in brackets. So we've got a fraction here, so let's consider our methods for fractions. Well, our denominator is raised to the power of 1, so we're not going to use indice laws. So let's check for the natural logarithm and the reverse chain rule. If I differentiate 3x subtract 2, I would get 3. If I compare that 3 to my numerator, well, they're numerical multiples of each other. To get from 3 to 1, we would multiply by a third. So I'm going to use that 1/3 in my final answer. It's going to be 1/3 of the natural logarithm of the modulus of our denominator, 3x subtract 2. Close my modulus and my brackets. And then we're going to put plus c. But the last thing I'm going to do is just multiply by the negative 2 over 3. So I would get 5 over 3x. And then negative 2 over 3 times 1/3 would be negative 2/9 of the natural logarithm of the modulus of 3x subtract 2, and then plus c like that. And that would be the final answer to the initial integral.